In this section, we're going to discuss L'Hopital's rule. You may recall in the past when we were taking a limit and we substituted the value of a into the function, we sometimes got what we called an indeterminate form of 0 divided by 0. Because we got 0 divided by 0, we know the function does not exist at the point a, but it is still possible that the limit exists. Unfortunately, with an indeterminate form, well, it can't be determined. Sometimes it exists, and sometimes it does not. In this particular section, we're actually going to be studying 7 different types of indeterminate forms. There are 2 basic indeterminate forms, 0 over 0, which we have seen before, and infinity over infinity. We'll talk more about why these are indeterminate forms and where they come from later in this video. There are also 5 other forms. 2 are arithmetic, that would be 0 times infinity and infinity minus infinity. And 3 of them are what we call power forms. 1 to the infinity power, 0 to the 0 power, and infinity to the 0 power. All of these, if they're obtained after substituting the value of the limit into the function, could represent a limit that exists or one that does not. We're going to learn a very important technique called L'Hopital's rule, which only applies to the 2 basic forms, 0 divided by 0 and infinity divided by infinity. We're going to have to learn how to convert the other 5 into one of those 2 basic forms so we can apply L'Hopital's rule in order to find the value of the limit. In order for this to happen, our function will have to be written in the form of a fraction, and both the numerator and denominator will have to be differentiable. Let me share my screen with you and we'll get started. Let's talk about the learning objectives. We need to recognize when we can and when we cannot apply L'Hopital's rule. It can only be applied in very specific conditions. We'll need to be able to identify all 7 indeterminate forms produced by quotients, products, subtractions, and powers, and then how to convert every indeterminate form to one of the basic 2 so that we can apply L'Hopital's rule to find the value of the limit if it exists. Then finally, at the end of this section, we'll discuss what are called the relative growth rates for functions. This will make your life much simpler when evaluating end behavior of a function. The limit as x goes to infinity or as x goes to negative infinity. Let's take a look again at the 7 indeterminate forms that we have. They are 0 divided by 0 and infinity divided by infinity, the 2 basic forms or primary forms to which L'Hopital's rule directly applies. Then we have 0 times infinity and infinity minus infinity, which have to be converted into one of the 2 basic. We have 3 power forms, 1 to the infinity power, 0 to the 0, and infinity to the 0. Now, of course, infinity is not a number, so what we're really saying is that when we put in the limit, whatever is in the function is approaching infinity, or it's approaching 0. Now let's take a look at the 2 basic indeterminate forms. These are the only forms to which we can directly apply L'Hopital's rule. Everything else has to be transformed into them. Notice also that the notation 0 divided by 0 does not mean we are actually dividing 0 by 0. That's not allowed. However, it means that the limit values as x gets closer to a are approaching 0 in the numerator and 0 in the denominator. The limit values are approaching 0 divided by 0. In fact, what we have is the limit of a function approaching 0 in the numerator divided by the limit of another function in the denominator also approaching 0. In other words, we really have the quotient of two limits. Each limit individually is approaching 0. We have something similar for infinity over infinity. We have the quotient of two limits, each of which is approaching either positive infinity or negative infinity. And we'll look at all combinations of signs. Now, why is 0 divided by 0 an indeterminate form? Normally, when we divide a number by itself, like 2 divided by 2, we get the number 1. But we know that thou shalt not divide by 0, so 0 divided by 0 cannot be 1. Why is this the case? Where is this coming from? Well, we'll see in a moment that it comes from the definition of negative exponents. Now, the next thing we want to look at is why infinity divided by infinity is such a problem. The deal is there's a thing called cardinality. Cardinality represents this magnitude of infinity that you have. There are different sizes of infinity. If you want to talk about the counting numbers or the rational numbers, ratios of two integers, those happen to be countable sets. They're infinite, but they're countable. But the irrational numbers, to which pi and e and the square root of 2 belong, those are not countable. They're a size larger than the integers themselves. In fact, they are something that we sometimes refer to as Aleph 1, but you don't need to remember that. Basically, there are different magnitudes of infinity. Some are much larger than others. Then, when we think about infinity divided by infinity, we have a problem. If the infinity in the numerator is a magnitude larger than the infinity in the denominator, it's going to pull it in the direction of the infinity in the numerator. But if the infinity in the denominator is a magnitude larger than the one in the numerator, it will pull the limit to 0. Now, what happens if they're roughly the same magnitude of infinity? Well, then anything can happen. It can grind to a halt at any of the real numbers. This is why infinity divided by infinity is considered indeterminate. We don't know what happens. We can't determine it, so it's indeterminate. Now let's talk a little bit about 0 times infinity and infinity minus infinity. When we look at 0 times infinity, we have a tug of war going on. Normally, 0 times any number is 0. But when you multiply by something that's wanting to pull it to infinity, you have a tug of war going on. Which one ends up winning can't be determined. So it's indeterminate. When we think about infinity minus infinity, we have the same issue that we had with infinity divided by infinity. Depending on which infinity has a larger magnitude, it will pull it in that direction. Or if they're of the same magnitude, it can grind to a halt at any real value. Or these limits could not exist. That means that these are both indeterminate as well. L'Hopital's rule cannot be applied directly to 0 times infinity or infinity minus infinity. Instead, we have to convert them to the two basic forms. We'll use some algebraic techniques in order to do that. In fact, sometimes it's just as simple as write it as a single fraction, and that's the algebraic technique. Now let's take a closer look here at the power forms, 0 to the 0, infinity to the 0, and 1 to the infinity power. These are not determined. We don't know what their limit values will be if they exist. Why is that? As I said, 0 to the 0 has a problem because of the definition of negative exponents. Let's come down here and look at what we've got. We have the number 1 equal to 5 to the first divided by 5 to the first. But by the rules of exponents, we know that when we're dividing, we subtract the powers. This gives us the definition of the negative exponents, but it also gives us 5 to the 0th power. In other words, the 0th power represents dividing a number raised to the first power by itself. And if we do that with 0, we're right back to the basic form 0 divided by 0. 0 to the first divided by 0 to the first does not exist. The limit of it is indeterminate. Let's now talk about infinity. If we think about infinity divided by infinity, and we raise infinity to the first power, if such a thing happens, again, we get infinity to the 1 minus 1, which is infinity to the 0, by the definition of exponent rules. But that means that infinity over infinity and infinity to the 0th power must both be indeterminate, and they are. Now, why is 1 to the infinite power indeterminate? That's a more difficult question, and I'm afraid I don't have a great answer for you. It is weird that 0 to the infinite power is in fact 0. 0 times itself infinitely often does give you the number 0. But 1 times itself infinitely often is not necessarily 1. There's no easy way to explain it except to work examples where the limit of the form 1 to the infinity comes out to different values, which establishes that it must be indeterminate. The best I can say is that when you're starting with a non-zero number and you're repeating multiplication infinitely often, weird things can happen. Let's now take a look at some forms that are not indeterminate. If we're going to talk about indeterminate forms, we also need to talk about the ones that we know the value for, so we don't mistake one for another. You cannot use L'Hopital's rule unless it's one of the 7 indeterminate forms. So what are the forms that can be determined? Let's take a look at some of those now. Now, obviously, if you substitute the value of a into the function and you get a finite real number, well, then the limit exists and that's the value of the limit. That's determined. Also, if you apply some of the techniques that we learned in chapter 2, such as factoring and reducing a rational function, or multiplying by a conjugate and then reducing by canceling a like factor, if you get a finite real number, then that is the value of the limit, and it is determined. There are some, however, that we will not be able to evaluate in that way, but some of those, L'Hopital's rule will apply. There are some others that we've looked at as well when we studied section 4.6, part 1. In fact, we learned that if we had a constant in the numerator, but the denominator was approaching infinity, then it got driven down towards 0. Let's take a look at all of these different ones that do exist and are determined. If you have a limit and it starts to approach 0 in the numerator and either infinity or negative infinity in the denominator, then the value of the limit is the number 0. Bottom is growing large in absolute value. The numerator is getting smaller, which in a fraction drives it towards 0. Whether it approaches from below 0 or above depends on which side of 0 you're approaching from and whether you have approached positive infinity or negative infinity in the denominator. Here's an example of one of those. The limit as x approaches infinity of the sine of 1 over x divided by x squared. We know that if we were to substitute an infinite power here, 1 divided by infinity would be 0. And the sine of 0 is 0. But we know that x squared as x goes to infinity goes up. The graph looks like this. And on the far right, it goes to infinity. This gives us the form of infinity over, or 0 over positive infinity, which is 0. What about 0 to the infinite power? Well, it has the limit of 0. Here's an example of that particular problem. The natural log of 1 over x plus 1, all of which is raised to the x power as x approaches infinity. We know as x approaches infinity, 1 divided by infinity goes to 0, but the natural log of 1 is 0, so we have 0 to the infinity power. Since x is a line and it approaches infinity as x goes to infinity. This does approach 0. You can graph it and look at it. You'll see that it gets there relatively quickly. Let's suppose you have any finite constant, c divided by something approaching infinity. This is going to approach 0. For example, the limit as x approaches infinity of 4 divided by x, the denominator gets larger and larger, but the numerator stays fixed. This will definitely approach the value of 0. Any limit where you substitute the value that x is approaching into the function and get a finite real number, well, that's the value of the limit. The limit as x approaches 3 of x plus 4 equals 7. Well, we substitute 3 for x and got 7. 7 is the value of the limit. What about limits where we perform algebraic manipulations until we can substitute for x to obtain a real number? For example, the limit as x approaches 2 of the quantity x minus 2 divided by the quantity x squared minus 4. You can factor the denominator. Note that this would give you the form 0 divided by 0 in the initial step, but by factoring, you're able to cancel the like factor x minus 2 and then substitute the a value of 2 into the reduced fraction to get the value of the limit, which is 1/4. All of these are determined, and we know what their limit values are. There are others that are not indeterminate, but they do not exist because they approach positive or negative infinity. They're not indeterminate, they just don't exist. They either approach infinity or negative infinity. Let's take a look at the ones that don't exist because they approach one of the infinities. Let's suppose that you took a limit and the function in the numerator approached infinity. The function in the denominator approached 0. So the numerator is getting larger and larger in absolute value, and the denominator is getting smaller and smaller. This will cause the magnitude to blow up to infinity. Whether it's positive or negative infinity depends on whether it's approaching positive infinity or negative infinity, and which side of 0 the limit is approaching from. If it's positive infinity, but you're approaching 0 from the left, it will go to negative infinity. If it's a positive infinity and you're approaching 0 from the positive side, the right, it will be positive infinity. If you were approaching negative infinity in the numerator and approaching 0 from the left in the denominator, it would be positive infinity because a double negative is positive. It approaches negative infinity in the numerator but approaches 0 from the right side, the positive numbers, it would approach negative infinity. There are some others that also tend to infinity. The limit does not exist because infinity is not a finite real number. This would be positive infinity times positive infinity, which, as you might expect, goes to positive infinity. Negative infinity times negative infinity, well, a double negative gives us positive. It also goes to positive infinity. And positive infinity times negative infinity, yeah, you're right, it goes to negative infinity. Adding and subtracting is problematic when one is positive and one is negative, but that's not the case with the ones we see here. If one function wants to go to positive infinity and you're adding another function that also wants to go to positive infinity, then it will go to positive infinity. If both functions want to go to negative infinity, it will go to negative infinity. If one wants to go to positive infinity, but you subtract one wanting to go to negative infinity, the double negative makes them both positive, so it approaches positive infinity again. In none of these cases do they have opposite signs. That is indeterminate. We have a last set that is determined, and that's when the numerator is a constant, like 5, and the denominator is approaching 0. It's not at 0, but it's getting close to 0. If we have a positive constant and we approach 0 from the right, it goes to positive infinity. As the denominator gets smaller, the fraction gets larger. If the constant is positive, 7, and we're approaching 0 from the left side, then it goes to negative infinity. And you can work out the signs on the last two. Now that we've talked a lot about what L'Hopital's rule applies to and what it does not apply to, let's actually start talking about how to apply L'Hopital's rule. Again, if you don't have one of these 7 forms, L'Hopital's rule cannot be used. Let's now look at the theory behind L'Hopital's rule. The theory behind L'Hopital's rule comes from the local linear approximation function. That's right, the tangent line. So let's take a look at what we have. As long as the function is differentiable at a, then we know we have a tangent line at a unique tangent line. We can approximate the function values near a by using the value on the tangent line instead, so that f of x on the true function is approximately equal to the y value on the tangent line. When we apply L'Hopital's rule, it always has to be applied to a quotient, function in the numerator and a function in the denominator. So we have 2 functions, f and g, that we're going to approximate with the tangent line. That means that their ratio, f of x divided by g of x, is approximately equal to the ratio of their tangent lines, as long as I'm close to a. Now, if I'm looking at this right here, then I know that I can approximate f of x over g of x. So it makes sense that the limit, as I'm approaching some value of f of x over g of x, would be approximately the value of the limit as x approaches the same value of the ratio of the tangent functions. Let's take a look now at the graph so we can see these different functions. The true function is here in dark blue. It's an increasing function from left to right. We have 2 functions whose ratio give us this graph, f of x and g of x. At the point A, we have an intersection of all 3 graphs. The tangent line at A on F and the tangent line at A on G. And they intersect the function that you see here. We have both the function G and the function F and the two tangent lines to the two functions at that point. Now, what can we say about this? Because we know the derivative exists at A, then we know it has to be continuous. If it's differentiable, then it's continuous. If it's continuous at A, and by the definition of continuity, function exists, the two-sided limit exists, and they're equal. That means that f of A is the limit as x approaches A of f of x. And we can say the same thing for G. G of A must be the limit as x approaches A of G of x. However, if we have the indeterminate form 0 divided by 0, both f of A and G of A have to be 0. So we know f of A and G of A are 0. So when we look at the limit of the ratio of the function f to g, and we approximate it with the ratio of the tangent lines, the constants f of A and g of A are both 0, so that part drops out. What's left is the derivative of f times x minus a divided by the derivative of g times x minus a. You're right. All unburied pluses and minuses are gone. So now we can cancel the common factor x minus a, which tells us it's got to be approximately the limit of the ratio of their derivatives. Now, we are not applying the quotient rule. We're saying because the function is differentiable at A, we can approximate the values with the tangent lines near A. And the ratio of f of x to g of x must be approximately the same as the ratio of the derivative of f to the derivative of g. In fact, they're equal. L'Hopital's rule can actually be applied over and over and over again within the same problem, provided the conditions are met, that you have the ratio of two functions, both of which are differentiable. Let's now go ahead and formally state L'Hopital's rule. Suppose f and g are differentiable functions over an open interval containing A, except possibly at A. It may not be differentiable at A. It may not even be defined at A. But other than at A, we know that it is a differentiable function on an open interval around A. If we know that the limit as x approaches A of both f of x and g of x is 0, then we can say that the limit of the ratio of f to g is equal to the limit of the ratio of their derivatives. Now, this assumes that the limit on the right exists, is a finite real number, or is infinity or negative infinity. This definition of L'Hopital's rule also holds for one-sided limits. Instead of x approaching A, we could have x approach A from the right or from the left. In fact, we can have x approach infinity or negative infinity, and L'Hopital's rule still holds. Let's take a look at a proof of part of L'Hopital's rule. We won't prove all cases, but we'll prove the basic one. We're going to look at the special case where we know that the function f and g are continuous on an open interval containing A. Have to be because it's differentiable. We're also going to assume that f prime and g prime are also continuous on the interval. We're told that the limit of the function, both f and g, as x approaches A, is 0. This gave us that indeterminate form 0 divided by 0. And we know by the definition of continuity, that means f of a and g of a are both equal to 0. That means that we can write the limit of f of x divided by g of x equal to the limit of f of x minus 0 divided by g of x. Subtracting 0 from anything does not change the representation. The next thing we want to do, since we know that f of a is 0, is replace the 0 in the numerator with f of a, very tricky, and replace the 0 in the denominator with g of a. You can probably predict what's starting to come out here. We're going to build the definition of the derivative in the XA format. What we need next is for each of these to be divided by x minus a. So we multiply by 1 in the form of 1 over x minus a divided by itself. This gives us the limit of the difference quotient with f over the difference quotient with g in the denominator. Then we can use the limit laws that say the limit of a quotient is the quotient of the limits to split the limits apart. But the numerator is the definition of f prime, and the denominator is the definition of g prime, which tells us that we have f prime of a over g prime of a. However, we also assumed that f prime and g prime were continuous. If they're continuous, then the two-sided limit exists, and the value exists, and they're equal. So we can rewrite f prime of a as the limit as x approaches a of f prime of x, and g of a, g prime of a, as the limit as x approaches a of g prime of x. And then we can reverse the limit law and say that the quotient of two limits is the limit of the quotient, which gives us the final result. Again, note that we are evaluating the limit of the quotient of f and g, their ratio, by instead evaluating the limit of their derivatives, f prime divided by g prime. We are absolutely not applying the quotient rule. That would be f prime g minus g prime f over g squared. L'Hopital's rule has nothing to do with that. We are instead using local linearity and saying that the limit of the ratio of two functions that are differentiable around a, except maybe at a, must be equal to the limit of the ratio of their derivatives. One step inside of taking the limit is important, and that is writing the L'H. The one step where you apply L'Hopital's rule by taking the derivative of the numerator function and the derivative of the denominator function. The equals just before that needs an L'H over it to indicate that you are applying L'Hopital's rule. Without L'Hopital's rule, the statement that they're equal is not true. They're only true under local linearity and L'Hopital's rule. This is required. Don't forget to do it. Let's now take a look at an example of one that we solved previously with an arithmetic method by factoring the denominator and canceling the common factor. We want to first identify the indeterminate form, so we substitute a into the function, and we get 0 over 0. This is an indeterminate form, so we're going to write that the limit that we're given under L'Hopital's rule is the same as the limit of their derivatives. Notice the L'H that appears over the equal sign just before I take the derivatives. The derivative of x minus a is 1. And the derivative of x squared minus a squared is 2x. Once I've applied L'Hopital's rule, I again try to substitute what the limit is approaching into the function. This case, I get a result, 1 over 2a. And this is, in fact, the value of the limit. Pretty neat, huh? All right, let's take a look at example 2. In example 2, we again want to identify the indeterminate form. X is approaching 0, so we substitute 0 in place of the variable x. And this gives us 0 minus 0 over 0, which is the indeterminate 0 over 0 form. I always look for this step when I'm grading problems. It must be there to justify using L'Hopital's rule. Now we're going to rewrite the limit, and we're going to apply L'Hopital's rule. This is a limit that we would not have been able to solve previously by any of the methods that we learned. The derivative of sine of x is cosine of x. The derivative of x is 1, and the derivative of x squared is 2x. I've applied L'Hopital's rule, and now I try to evaluate the limit again by substituting what the limit is approaching in place of the variable x. This will give me cosine of 0 minus 1 over 2 times 0. The cosine of 0 is 1, and this again gives me 0 over 0. But I happen to know that cosine of x minus 1 is differentiable near 0, and so is 2x. So I can apply L'Hopital's rule, again. I put another L'H, and now I apply L'Hopital's rule again by taking the derivative of the numerator and dividing by the derivative of the denominator. Then I substitute the value back into the function to see if I get a real number, or infinity or negative infinity. This gives me negative 0 divided by 2, which is 0. And that's the value. Let's now take a look at example 3. In example 3, you're evaluating the limit as x approaches 0 of sine x over x. Sine of 0 is 0, and that would give you 0 over 0 when you substitute 0 in place of x. You're going to use L'Hopital's rule to solve this one. Go ahead and pause the video, then turn it back on when you've completed the problem. I hope you got the value of 1. We know we have form 0 divided by 0, so we can directly apply L'Hopital's rule. Taking the derivative of numerator and denominator separately gives us cosine x over 1, and the cosine of 0 is 1. Let's now move to the next page. Go ahead and pause the video while you evaluate the two limits in example 4 and 5. Then turn the video back on and we'll talk about the result. Here in example 4, we get the form 0 over 0. So we apply L'Hopital's rule to get sine x over 1, and then we resubstitute the value that the limit is approaching to end up with the value of 0 for the value of the limit. Now, the function does not exist at 0. The limit does, and it looks like the function is going to hit the y value of 0. Looking at example 5, notice that we are approaching 0 from the right. This is because the square root of x is not defined on the left. So the two-sided limit would not exist, so we need to approach from the side where it's defined, which is from the right. The tangent of 0, since it's sine divided by cosine, is 0, and the square root of 0 is 0, so we get the indeterminate 0 divided by 0 form. Then we can directly apply L'Hopital's rule to get secant squared divided by 1 over 2 the square root of x. Secant squared is 1 over cosine squared, and because the 2 square root is in the denominator of the denominator, it moves to the numerator. I've applied L'Hopital's rule once. My next step is to resubstitute the value of 0 and see if I get a finite real number. Here you can see that I get 0 divided by 1, which is 0. Again, this function does not exist at 0, but it looks like it hits the value of 0. Let's now turn our attention to the next two. Tangent of 4x divided by tangent of 7x, and the ratio of two polynomials in a rational function. In this particular case, you want to go ahead and substitute what the limit is approaching to make sure that you can apply L'Hopital's rule. Pause the video now to work it out. Let's go ahead and discuss example 6. This is one that we did learn to do in chapter 2, but it was quite difficult. It took a lot of work and a lot of algebra. Notice here that when we replace x with 0, we get the tangent of 0 over the tangent of 0. Do not make the mistake of thinking that is 1. Tangent of 0 is 0. 0 divided by 0 is not 1. It's undefined. And in a limit, it's indeterminate. That means we can apply L'Hopital's rule. And remember to apply the chain rule. Derivative of tangent is secant squared. And then we have to multiply by the derivative of the argument as the chain rule. I don't tend to do well with secant, so I converted them to cosine forms. Notice that the 4 and the 7 stayed put, but secant squared of 4x dropped to the denominator to become cosine squared of 4x, and secant squared of 7x in the denominator rose to the numerator to become cosine squared of 7x. Again, I've done something. I applied L'Hopital's rule, so I need to substitute the value that the limit is approaching, x is approaching 0, back into the function to see if I get a finite real number. And in fact, I get 4 7s. Much simpler than the method that we had to employ in chapter 2. Looking now at example 7, we have the ratio of two polynomials. You must go ahead and substitute the value that the limit is approaching, -1, first. When you do that, notice that you do get indeterminate basic 0 over 0 form. And because of that, you can apply L'Hopital's rule. The denominator's derivative is 1, and you have the derivative of the numerator polynomial. Then you substitute -1 in again, and you get 1 for the value of the limit. The function does not exist at -1, but the two-sided limit does, and it's pointing to a y value of 1. Go ahead and pause the video and work out our last example in this section, which is the limit as x approaches 3 of x squared minus 9 divided by x minus 3. This is also one that we had a technique to solve in chapter 2. But now that we know we have L'Hopital's rule, we know those are differentiable functions, we can definitely apply L'Hopital's rule if we get an indeterminate basic form. Let's go ahead and look at the result for example 8. In example 8, substituting that the limit is approaching 3, I get the indeterminate 0 divided by 0 form. So I apply L'Hopital's rule to the original limit, and I obtain the limit as x approaches 3 of 2x. And I substitute 3 for x, I get that the y value that it looks like it hits is 6. Let's now take a look at the theory behind L'Hopital's rule in the other basic form, infinity divided by infinity, so we can establish that it also works here. We start with the same rules that we needed for the 0 divided by 0 form. F and g are both differentiable functions on an open interval containing a, but they may not be differentiable at a. They could be, we just don't know, and it doesn't matter. If the limit as x approaches a of f of x is either infinity or negative infinity, and the limit as x approaches a of g of x is also infinity or negative infinity, no, the signs don't have to match, then it turns out that the limit of the ratio of f to g is equal to the limit of the ratio of their first derivatives. L'Hopital's rule still applies, assuming that limit exists or becomes infinity or negative infinity. The result also holds if we consider one-sided limits as x approaches a from the right or the left, and it also works for end behavior, x approaching infinity or negative infinity. Let's go ahead now and look at some examples for how to apply this one. When we think about the function in example 9, we have natural log of x divided by x squared. Let's think about the graph of those two functions. When I think about natural log of x, I know that it approaches 0 from the right, and then it crosses at 1, 0, and then it grows ever so slowly to infinity. The limit of natural log as x goes to infinity is infinity. I also know what the graph of x squared looks like. As x goes to infinity, the graph definitely goes to infinity. That means that I can say that I have the form infinity over infinity as x is approaching infinity. Because it is one of the basic forms, I can apply L'Hopital's rule. First, rewrite the original limit before you apply L'Hopital's rule. You have to have the L'H on the equal sign between them. By L'Hopital's rule, this has to be equivalent to the derivative of natural log, which is 1 divided by x, over the derivative of x squared, which is 2x. Keep track of which bar is the primary division bar. The primary one is the one I drew longest. Beneath the 2x, there's actually a 1, which if it helps, you can write like that. Notice that x in the numerator is in the denominator of the numerator, and the 2x is in the numerator of the denominator, which means they're both in the denominator. This gives you the limit of 1 divided by 2x squared. Now, what happens as x goes to infinity? Infinity squared is infinity. Times 2 is double that. The denominator is growing very, very large, while the numerator stays fixed at 1. This is a form that is determined. When we have a constant over something approaching infinity, we know that we're going to 0. Let's take a look now at example 10. In example 10, we have the ratio of 2 cubic functions. We know from what we did earlier in section 4.6 that the end behavior is going to be the ratio of the 2 highest degree terms. In this case, 4x cubed divided by 2x cubed. We know the limit should be 2. Instead of doing it that way, let's apply L'Hopital's rule and see why that worked. Go ahead and pause the video to work it out now. Let's examine example 10. Notice that because they're both cubic and both have positive leading coefficients, they're both going up to the right. Now, perhaps there's a wiggle in the middle, we don't know. But as x goes to infinity, both the numerator and denominator go to infinity. You can apply L'Hopital's rule, which produces a quadratic equation in both the numerator and denominator, both with positive leading coefficients. But again, we know that quadratics that have positive leading coefficients on the right as x goes to infinity go to positive infinity. So we have form infinity over infinity again. So we apply L'Hopital's rule again, obtaining two linear functions. But these linear functions have positive slope, which means that they're slanted uphill. As x goes to positive infinity to the right, both lines go to positive infinity. So we have infinity divided by infinity again. We apply L'Hopital's rule again. Again, in each case, we're checking to make sure that the function in the numerator and denominator is differentiable. And these are all polynomials. They're differentiable everywhere. Finally, we obtain the ratio of 24 to 12, which is 2, which is what we expected. Now, that's the last example that I wanted to work in this first part of section 4.8, where we were just talking about the two basic forms, 0 divided by 0 and infinity divided by infinity. Those are the only indeterminate forms to which you can directly apply L'Hopital's rule. There are 5 others that we'll study, but we have to convert them first. Let's now turn our attention to converting the two arithmetic forms, 0 times infinity and infinity minus infinity, into one of our two basics. In general, when we want to convert 0 times infinity or infinity minus infinity into one of the basic forms, we have to get them written as a single fraction, because L'Hopital's rule applies to the ratio of two functions in a single fraction. So we take a look at what we have and try to imagine how we can convert these two into a fraction. Let's look at 0 times infinity first. We can take the fact that multiplying by a value is the same as dividing by its reciprocal, and I have an error here. That should be dividing. Multiplying by a value is the same as dividing by its reciprocal. I'll make sure I get that fixed. In other words, if I want to multiply by 2, it's the same as dividing by 1/2, because the denominator of the denominator is the numerator. We can take the original first factor, which had the 0 limit, and divide by its reciprocal, which would give us 1 over 0. If we had that, then we would still have the infinity in the numerator and 1 divided by 0 in the denominator. But when the denominator is approaching 0 and the 1 above it is fixed, we know that 1 over 0 approaches infinity, which gives us infinity over infinity, one of the two basic forms. I can also choose to move the second factor by dividing by its reciprocal. For example, if I had the form 0 times infinity, I could leave the 0 in the numerator and divide by 1 divided by infinity, the reciprocal of infinity. However, if the numerator is fixed at 1 and the denominator is going to infinity, I know this will drive it to 0, which gives us the indeterminate basic form 0 over 0. So what we do is we take one of the factors, either the one giving us 0 or the one giving us infinity. We divide by its reciprocal. That creates a fraction and gives us one of the two basic forms. In theory, it doesn't matter which one you move. In practice, one is often simpler than the other, and you never move natural log. Leave natural log where it is and move the other factor. When you move natural log, you turn a, complicated problem into an extremely complicated problem. So for example, if we're looking at the limit as x approaches 0 from the right of x times natural log of x, where x would be approaching the value of 0, and natural log would be approaching the value of negative infinity, we will leave natural log in the numerator and divide by the reciprocal of x, 1 over x. Then we will again evaluate, and in this case, as x goes to 0, I get infinity over infinity, negative infinity over positive infinity. Let's go ahead and apply this version of L'Hopital's rule now. We're going to identify the indeterminate form, then use L'Hopital's rule to evaluate, as we've done before. In this case, I'm substituting 0 from the right in place of my variable x. Remember that cotangent is cosine divided by sine. This is going to give me 0 times 1 divided by 0, which gives me the form 0 times infinity. Because I'm approaching from the right, positive infinity. Now I'm going to take the reciprocal of one of them and divide by it. In this case, however, I note that I have a trig function, and I could, if I wanted, simply write it in terms of cosine and sine. That would give me a fraction. Let's see if it gives me one of the two basic forms. If I rewrite, I can obtain the following. Note this is not actually applying L'Hopital's rule yet. Instead, I'm simply rewriting cotangent as the ratio of cosine to sine. Now when I try to substitute, I have 0 times the cosine of 0 divided by the sine of 0, which gives me 0 times 1 over 0, which is 0 over 0, which is in fact one of the two basic indeterminate forms. Now I can apply L'Hopital's rule. I want you to pause the video and work it out, and turn the video back on, and we'll compare. Note that you are going to have to apply the product rule. Let's now look at example 11. I applied the product rule in the numerator because I knew x and cosine x were differentiable near 0, and sine of x is also differentiable at 0. And this gave me the representation in the numerator. Then I simplified, and then I substituted the value that the limit was approaching in place of the variable. This gave me 1 for the value of the limit. Let's now turn our attention to example 12 and 13. In example 12, I have the limit as x approaches infinity of x squared times e to the negative x. X squared goes up forever, so it's approaching infinity. E to the negative x, as x moves to the right, is a decreasing exponential, which approaches 0. That gives me infinity times 0. In this case, since the exponential has a negative exponent, it makes sense to simply drop it to the denominator and change the sign to a positive. In example 13, I have the limit as x approaches infinity of x times the sine of 1 over x. I know x is a slanted line, which will go to infinity, but 1 over x will approach 0, and the sine of 0 is 0. Again, I have infinity times 0. In this case, moving the sine of 1 over x would make it more complicated. So let's move x by dividing by the reciprocal 1 over x. Yes, it'll be complex, but I know you can handle it. Go ahead and pause the video, work it out, and turn it back on to compare. In example 12, note that the graph of x squared, x goes to infinity, and y goes to infinity. In the graph of e to the negative x, as x goes to infinity, y goes to 0. Now looking at this, we have the limit of x squared times e to the negative x, which we can rewrite as the limit of x squared over e to the x. The original is infinity times 0, but by moving the exponential, we've converted it to a fraction, so we reevaluate. X squared goes to infinity again, but e to the x also goes to infinity. So we have the basic form infinity over infinity. We apply L'Hopital's rule once to get a line over an exponential, which again invokes L'Hopital's rule. Remember that e to the x is differentiable everywhere, and polynomials are differentiable everywhere. Applying again, we get 2 over e to the x. E to the x we know goes to infinity. 2 is fixed. As the denominator gets larger, it drives it to 0. Let's now look at example 13. In example 13, we had x times sine of 1 divided by x. We know that this gives us infinity times 0, since 1 over infinity is 0. The sine of 0 is 0. In this case, moving sine would turn it into cosecant, which would make it more difficult. So instead, we're going to move the x by dividing by 1 over x. This converts it into a fraction, so we reevaluate the form. The sine again goes to 0, and 1 divided by infinity also goes to 0. So we have the basic form 0 over 0. We apply L'Hopital's using chain rule, and notice that you get the same factor in both numerator and denominator. Remember, you can write 1 divided by x as x to the negative 1 power. The common factors cancel, and you take the limit of the cosine of 1 over x. As x goes to infinity, 1 over infinity goes to 0. Cosine of 0 is 1. This is the last one that I wanted to do for this type. Let's now look at converting infinity minus infinity. To be honest, these are harder and more tricky. There are a couple of techniques that we can use. Some of these require very convoluted algebraic methods, and we'll not employ those. We're looking for basic solutions, although you may not feel like they're basic once you see what we have to do. One of them is, if they're trig functions, try writing them in terms of sine and cosine, and see if this results in some common fraction form. In other words, get a common denominator and combine. If they're not trig functions, but you think you could get a common denominator and combine the two terms, do that. If there's no suitable common denominator, then you're going to multiply both terms by a form of 1, either 1 over x divided by 1 over x, or 1 over x squared divided by 1 over x squared, depending on what you have in the function. This will give a common denominator of either 1 over x or 1 over x squared. There will probably be some reduction that can happen. that will create a common basic form. Let's take a look at example 14. In example 14, we have the limit as x approaches infinity of x minus the square root of x squared plus 1. We know that x is a slanted line that goes to infinity as x goes to infinity. And the square root of x squared plus 1 is the square root that also goes to infinity. We have the form infinity minus infinity. Because there are different sizes of infinity, we don't know which way it goes, or if it grinds to a halt at a finite real number. What we're going to do is we're going to try to turn it into a fraction. In this case, it's not trig, and there's no obvious denominator. I do have x to the first on the outside, so I'm going to choose to multiply by 1 over x over 1 over x. I'll leave the 1 over x in the denominator to serve as a single fraction. In the numerator, note that you have to distribute the 1 over x to each term. After distributing, I end up with something that looks like this. I need to get in basic indeterminate form. I know in the denominator I've got 0, so I'm going to try to get 0 out of the numerator. You want to take the x, which is outside the square root, and move it under the square root by squaring it. Since x is approaching positive infinity, we know that all the values are eventually positive. And then we can write that this becomes the limit as x goes to infinity of 1 minus the square root of x squared plus 1 divided by x squared, all under the radical, and divided by 1 over x. Now I'm going to simplify what's under the square root by dividing each term in the numerator by the monomial single term denominator. This leads to the following form: 1 minus the square root of 1 plus 1 over x squared, all under the square root, divided by 1 over x. Now I'm going to go ahead and plug in again to see if I have an indeterminate form. In this case, when x approaches infinity, under the radical, I get 1 plus 1 over infinity squared, which is 1 plus 0. So I get the square root of 1, which is 1. 1 minus 1 is 0. And I know the denominator is going to 0. So I have the basic indeterminate form, 0 over 0. Now it's time to apply L'Hopital's rule. Go ahead and pause the video, complete the problem, then turn the video back on, and we'll talk about the result. I kind of ran out of room at the bottom, so it's a little cramped. When I look at this problem, again, what I'm going to do is I'm going to apply L'Hopital's rule after determining that I have a basic indeterminate form. As x approaches infinity, I got 0 over 0. Applying L'Hopital's rule, I take the derivative of the numerator and the derivative of the denominator. The numerator gives me negative 1 over 2 the square root of what was under the radical times the derivative of what was under the radical, which is negative 2x to the negative 3. The derivative of the denominator, x to the negative 1, gives me negative x to the negative 2. Now, I know that the x to the negative 3 will drop to the denominator of the numerator. The 2's in the numerator will cancel, and the negatives in the numerator will cancel. And I get 1 over x cubed, the square root of 1 plus 1 over x squared, under the radical. In the denominator, I had a negative x to the negative 2, which will move to the numerator as negative x squared. When I multiply, x squared and x cubed reduce, You get -1 over x times that radical. As x goes to infinity, 1 over x squared goes to 0, and I get the square root of 1, which is 1. I also have an x outside the radical, so I end up with -1 over infinity, which drives to 0. Let's take a look at one more example. We now have example 15. We again want to identify if we have an indeterminate form. Possible, use L'Hopital's rule. We have the limit as x approaches 0 from the right of 1 over x minus 1 over sine x. We know that as x approaches 0 from the right, we're going to get 1 over 0, but the values will all be positive, which means that it's going to be approaching infinity. The second one, the sine of 0 is 0, so 1 over 0 also approaches positive infinity, since sine is positive to the right of the origin. That means I have infinity minus infinity, which is definitely indeterminate. Go ahead and pause the video and try to work it out. In this problem, you're going to have to get a common denominator, which is going to be x sine x. Try that method, and let's see how you do. To solve example 15, I found the lowest common denominator, which was the product of the two denominators, x sine x. Then I multiplied each term by a form of 1 in the factor that it was missing from the lowest common denominator. Then I combined it into one fraction over the common denominator with the numerator sine x minus x. Because I now have a single fraction, I thought it was time to go ahead and reevaluate to see if I had a basic indeterminate form. That did result in 0 over 0. So I applied L'Hopital's rule, again noting that sine x and x sine x, are all differentiable functions. Then I took the derivative of the numerator and divided by the derivative of the denominator. In the denominator, I had to use the product rule. Again, I've done something, so I substitute what the limit is approaching again. This gave me, again, the form 0 divided by 0. I keep unplugging myself. The next step is to apply L'Hopital's rule once again. This gave us the product here. You'll see I had to use the product rule on the second term in the denominator, but not the first. This time when I substituted 0 in place of x, I ended up with 0 divided by 2, which is the number 0. This is the last example that we're going to work for the two arithmetic forms. What's left to cover are the power forms, but because this video is already getting long, I'm going to split it here. We'll cover the power forms in the next video. See you soon.